Hello guys, welcome on Tesla Adventures. Now, in previous video, we studied the force acting on a current carrying wire which is placed in uniform magnetic field. Now let us discuss further the applications of this concept. So you can see that we have already discussed that in a current carrying loop which is of circular shape placed in magnetic field, the uniform magnetic field, the net force acting on the loop would be zero. But if we imagine a situation in which this current carrying loop is placed in a magnetic field which is going inside the plane or coming outside the plane, and current is flowing like that, so you can see that the net force will be zero due to the fact that if we consider a small element on the wire like that, dl vector, then the force acting on this dl vector would be df in the perpendicular direction, and dl vector on the bottom will be like that, and the force acting would be like that. So this small forces will be cancelled out by each other, and the net force acting on the loop will be zero. But you can see that these forces are pulling this loop apart, and therefore they are creating some tension in the loop. So we have to find out that tension in the loop. So for that, let us consider a small element like that, and this is theta. Okay, so the small length dl will be equal to r d theta, and the force df will be I, if we write it down in vector form. So df will be I dl cross b, and we have already discussed that force will be acting in this direction. Now the direction of this force is obviously determined by the same Fleming's left hand rule which we used in determining the direction of the force in the case when charge was moving with velocity v, because that derivation which we discussed in the previous video is done by, or it is concluded by, the formula qvb. So the direction of this force is also governed by the same Fleming's left hand rule, in which if we stretch the first two fingers and thumb of our left hand mutually perpendicular, then that first finger would represent the direction of magnetic field, second finger would represent the direction of current flowing, and the thumb would represent the direction of force. So by that Fleming's left hand rule, I have concluded that force would be acting in this direction, and that force is given by this formula. And now if we have concluded that the direction of force would be like that, we just need to find out the magnitude. So df magnitude will be equal to I dl is r d theta, and b is magnetic field. So this would be the force, a small force acting on the small element of this ring. Now let us use a zoom or a enlarged view of this element for calculating the tension. So we know that tension will be acting tangentially like that, okay, and df would be acting like that in the upward direction. Okay, so you can see that if this angle is d theta by 2 and this angle is 90, so this angle would be 90 minus d theta by 2, and it would be d theta by 2, it would be d theta by 2. So the component of tension in the downward direction will be 2t sine d theta by 2, and therefore we can say that df will be equal to 2t sine d theta by 2. Okay, and df will be I lb, and l is r d theta, so this is r d theta into b, and for small angles we can write it down as 2t into d theta by 2, because we know that for small angles sine theta is almost equal to theta. So cancelling this 2 with 2 and this d theta with d theta, T is equal to I into R into B. And if we have given, it is given in the question that length of the wire is L, then we can replace the R by L is equal to 2 pi R. So R is equal to L by 2 pi. So T will be equal to I into LB divided by 2 pi. Okay, to just remember this formula directly in the exam, we can use a simple analogy that the total force acting on the total wire, if we just ignore the direction, if we just sum up the magnitudes of all the small forces dF, then the total force acting on this wire will be ILB, where L is the total length of the wire, and the force acting on the unit length would be the total force is distributed among 2 pi angle. This total angle is 2 pi. So if we need to find out the force acting on the unit angle, then it would be ILB upon 2 pi. And this is the same conclusion. So that tension will be equal to ILB upon 2 pi. Thank you.